Next we'll do is Williamson ether synthesis. This is a reaction between base and haloalkane. So we'll be taking RONA, or we can take ROK or whatsoever. So this RO part will be acting as a base and a nucleophile both. And we have RX. Now when we talk about RONA, Na is just a spectator ion. You can also treat it as RO minus and Na plus. And obviously your RO minus is much better nucleophile as compared to X over here. So this reaction will proceed through SN2 mechanism. This RO minus will do a back attack. This RO minus will do a back attack on R dash X, forming R dash OR. That means ether formation will take place and X minus will come out. This is simple SN2 mechanism. This is a stronger nucleophile. And this is a good leaving agent. This is a good leaving group. So in the presence of both, the reaction will go through SN2. RO minus will attack on R dash, will form ROR, and X minus will get removed. Now a thing to note over here is what R dash X cannot be. So R dash X cannot be a tertiary alkyl halide. It cannot be halide where X is attached on a bridgehead. It cannot be a vinylic alkyl halide, and it cannot be phenylic halide. These will have PDCH, partial double bond character. Tertiary will not do SN2, and on bridgehead also. These bridgehead also do not participate even in SN1 or SN2. So all of these will not go through SN2 reaction. In any other case, reaction will go forward normally. So now we'll do some questions based on Williamson ether synthesis, and we'll understand this furthermore. We'll try to see what all different cases can be formed using this reaction. Okay, so I'll just write down the questions, note them down, solve it quickly, and then I'll discuss. Now note down these questions, try solving it on your own, and then we'll discuss. There are a few other cases also which I'll discuss while explaining you the answer itself. Let's discuss now. So now this MEO minus will attack on Me through a back attack and will form MEOMe. SN2. This whole reaction is SN2. So whatever reactions are happening over there, all will happen through an SN2 mechanism. Now this again, MEO minus will attack on ET and will form ETOMe. Here also ETO minus will attack on Me, will form ETOMe. Now just note one thing. Let's assume for this particular reaction, rate is R1. Okay, and for this third reaction, the rate is R2. Now, which rate will be greater? Like, what will be the relation between R1 and R2? R1 will be greater towards SN1, or R2 will be greater. So the rate will be R2 greater than R1. Why? Though both of these are forming the same, both of the reactions are forming the same product, but SN2 mechanism is purely driven by the crowding on the carbon. If there is more crowding on the carbon, reaction rate becomes slower. So when we look at the carbon where leaving group is attached, this is ET, which is, and here it is Me. So this is ethyl group and this is methyl group, which is more crowded relatively. Ethyl group is more crowded as compared to methyl. So the reaction will be faster in this case as compared to this, though both are forming exactly same products. Okay. So these kind of questions have been asked many times when the products are forming same and you have to just compare the rate of the reaction. So you have to see where the attack is happening, where the nucleophile is attacking, what kind of carbon is it, whether the crowding is more or less. On that basis, you will be able to decide which rate will be faster and which will be slower. Now in this case, what will it form? Again, this will attack on this carbon, forming This will be the product formed. Now here CH3OPH. All of you quickly keep checking because there is nothing new. We just have to, the easiest reactions are SN2 reaction. We just have to replace the leaving group with a nucleophile. That's all. So there is no confusion with related to rearrangement and all. So it doesn't take much time to do it. Just quickly check your answers. Again, this PHO minus will attack on this CH2, forming PH, CH2O, PH. This O minus attacking on this CH2, forming. And wherever the inversion is possible, wherever there is a configuration, a change possible, there will be inversion will take place there. Again, this will attack over here, forming. So these will be the products formed. Just quickly check your answers. Which ones you have done wrong, which ones you have not done wrong. Now, let me just discuss few more cases with you. Let's talk about the case like okay. So we have this reaction, both one is path A and one is path B to form this product. This reaction is pathway A and this reaction is path B. Now tell me which path will be the best path according to Williamson ether synthesis to form this molecule. When we are talking about A, we have taken O minus with a carbon which is tertiary, whereas where the attack is going to happen, that is CH3Cl, and this is a very less crowded alkyl halide. Now look at the second case where we have taken CH3O minus as a base, and the carbon where we are going to attack, that is very crowded carbon, and this is a tertiary carbon. Over here we have already discussed in terms of Williamson synthesis that we cannot use tertiary RX. We cannot use the compounds where your X is attached on the bridge head. We cannot use where the PDCH is there. So this particular reaction, if you'll use this kind of RX for the reaction, in that case reaction will not proceed. So we will not get this as a product, and hence B pathway is a wrong method to form this particular ether. Similar way, if I take a reaction where again I am trying to follow two different pathways to achieve one product, and the possible product is this. Now what we have taken here is, in the first case where the pathway is A, we have taken O minus or alkoxide on the bridgehead carbon. We have taken O minus on the bridgehead carbon. So alkoxide is a bicyclo compound where O minus is on bridgehead, whereas alkyl halide is a primary alkyl halide. It could be a secondary alkyl halide also. Whereas in the other case we have taken alkoxide ion as CH3O minus, and we have taken chlorine on the bridgehead carbon. Now in this case, can we do SN2 reaction? No, we cannot. We have already discussed many times before that SN2, SN1, any reaction is not possible on the bridgehead carbon. Hence B pathway will not give you this product. Instead, if we'll follow the above one, where this bridgehead carbon with O minus is acting as a nucleophile, which will attack on the CH3. This way if you use, or this pathway if you follow, you will be able to get an ether with a bicyclo compound over which OCH3 is there. Okay, so just make sure whenever you have got the questions, whenever you have reactions given, or when you have to convert one compound to another, or if you have to convert an alcohol or haloalkane to ether, just make sure that you do not use wrong RX. We need to use the RX which can support SN2 reaction. We cannot use tertiary. We cannot use the RX which has PDCH. We cannot use bridgehead cyclo. We cannot use bridgehead bicyclo compounds, okay, bicyclohalide compounds. So these are some examples of Williamson synthesis. These are the answers for the questions given. Okay, one more thing which I probably missed while explaining SN2 reaction in Williamson ether synthesis, and that is the relative rate of reactivity towards SN2 for ether and RX. So let's say I have an ether and I have a RX. If I have to check which one will do more faster SN2 reaction, here our ether will do much faster reaction towards SN2 as compared to RX. Reason? First of all, when we are talking about this, there is lot of angle strain on ether. Okay, this epoxide has high amount of angle strain. Moreover, both the carbons will have a partial positive charge. So total partial positive charge on the carbons is more over here as compared to RX over here. So what we will see is we can get such kind of questions that we can get the questions where we have to compare the rate of reactivity of the molecule towards SN2. So always your epoxide will have a greater reactivity or higher reactivity towards SN2 as compared to haloalkane. And this is majorly due to the angle strain what your epoxide faces. Okay. So this is about Williamson ether synthesis. Next we'll be doing intramolecular SN2 reaction. Let's see what is intramolecular SN2 reaction is.